So today we're going to look at differential equation, but this time we're going to look at in the context of a question. So if we take this example, it's a rate of increase of population of microorganism at time t is given by this formula, dp dt is equal to 3p. Notice t has to be bigger than 0, and initially the population was of size 8. We want to find the model for p in the form p equals to a e to the power of 3t, stating the value of a. So here we got the rate given, dp dt equal to 3p. It's not the actual population, but it's the rate of increase of population. That's what the differentiation is saying. So if we multiply both sides by dt, we'll have dp is equal to 3p dt. And in the previous video, when we did the differential equation, we said how you could just separate the variable. So we could take the p over. So we have 1 over p dp is equal to 3 dt. And simply just put an integral symbol and integrate both sides. But we know the left hand side is ln p equals to 3t plus c. Now the constant of integration, you only need to add it to one side, since if you add it to both sides and you take it all over on one side, it's still going to give you another constant. So that's what the plus c is. We just add it to one side. So now if we take the inverse or e on both sides, e ln p will just give you p, and then e to the power of the whole thing. So p would equal to e to the power of 3t plus c. So we have a generic equation for the population. Because before that wasn't the population formula, it was the rate of change of population. So now we could use the indices rule. If we have e to the power of, or any exponential to the power of, and there's a sum, you can separate them using the indices rule by writing it as a product. And since c is a constant value, e or any exponential to the power of constant value is always going to be another constant, and we'll give that an arbitrary value. We'll call it capital A. So p would equal to ae to the power of 3t. So now we could use the boundary condition. We're told at the beginning the population size is 8. So whenever we're talking about initially, we set t equal to 0, because t is the time here. Initially time is 0. So if we replace t with 0 and p with 8, e to the power of 0 is just 1, so we'll have a equal to 8. So we could rewrite the complete equation now, p equal to 8 e to the power of 3t. So part B of this question, it says find to the nearest hundred the size of the population at time t is equal to 2. So now we have an equation. It's pretty straightforward. You just replace the t with 2, and that will give you the population. So if you just put that on the calculator, so once we plug this in the calculator, we get 3,227. Yeah. Okay, so as if we round it, because it's set to the nearest hundred, so it's just going to be 3,200. So always read the instruction carefully in the exam. If it says to the nearest hundred, they want the final answer to the nearest hundred. So there we have it. P is equal to 3,200. Now part C of this question, it says find the time at which the population will be 1,000 times at its starting value. So if it's 1,000 times its starting value, we know we started off with 8. So that means we want to know what value t will be when it's 8,000. So we just replace p with 8,000 because it says 1,000 times. 1,000 times 8, 8,000. Now using just a basic algebraic skills, we could just work that out.
Yeah.
So we'll divide both sides by 8. We take ln on both sides to get rid of the e. And then we just divide it by 3. So it gives us t of 2.3. So the time will be approximately 2 hours and 18 minutes. So bear in mind 2.3 is not 2 hours and 30 minutes. 3 would be 3 over 60 of an hour. So we need to be a bit careful. Or in the calculator you could just use the speech mark button and that'll convert it into hours and minutes. Okay, so part D of the question, it says state one limitation of this model for large values of t. Now, what do you think will happen as t gets bigger and bigger, as t gets towards infinity? So it's not possible for population to grow exponentially forever, since eventually they'll start running out of food or space. So that's one limitation. All right, so let's look at this question here. Okay, so here we have an example of a drum of a diameter 20 meters and the water inside it of height h. And we're told there's a leakage at the bottom of the drum, and the leakage is flowing at a rate which is proportional to cube root of the volume of the water. And we ask part A, show that after t minutes the tap is opened, the rate of change is minus k cube root of h, where k is some constant to be found. So let's think back to differentiation chapter on how we could write dh dt as product of the differentials. So we know dh dt, we could write this as dv dt times dh dv, because if you look at it diagonally, the dv's will cancel out. So that's another way of writing dh dt. So since dh dt can be written in this form, we are told what the volume is, and we can also work out the dv dh and then reciprocate that. So volume of a cylinder we know is pi r squared h. We could replace the r with 10 because the diameter is 20, so the radius must be 10. So the volume in terms of h is going to be 100 pi h. And we could differentiate that and work out what dv dh is. So dv dh is just 100 pi. Okay, so if we reciprocate that, invert this, so we'll have dh dv equal to 1 over 100 pi. Now, dv dt, we're told the water flows out of the bottom of the tank at a rate proportional to cube root of the volume. So if it's cube root of the volume, and since it's flowing out, we know there's going to be a negative involved at the rate. So we could write this as some constant, a negative, we'll call it c, so it'll be minus c cube root of v. So we could express this in this form because we know what v is. V is pi r squared h. We could replace the r with 10 and simplify. So we'll get dv dt equal to minus c cube root of 100 pi h. Now all we have to do, we have to be, first of all, we need to be careful. It's not c cubed, it's cube root. So it could quite be easily mistaken as c cubed, but it's cube root of 100 pi h. So we need to be careful here. We simply just replace the expression of what we found. So dh dt is equal to minus c cube root of 100 pi h times 1 over 100 pi. And if we separate the cube roots, we could write it like this. And the reason we're doing this is to help us to simplify this. So if I write in that form, I could group the constant terms together. So therefore, I have dh dt is equal to minus k cube root of h.
Yeah, I've got that.
So we could just say where k is c cube root of 100 pi over pi. So we replace all of this with a k. So it's nice and easy to work with. And the best thing about equations, if you look at most of the important equations, that change the world, you'll see it's always put into a nicer form, like f equal to ma or e equal to mc squared, all that sort of stuff. But if you actually open it up, it's quite a lengthy process. But it's not how messy the equation is, it's how much you could simplify. So you could see here we're able to simplify quite nicely. Okay, so part B of this question, it says show that general solution to the differential equation may be written in this form, where P and Q are constants. So if we go back to our dH dt equal to minus K cube root of H, and again in the exam, if you're not able to do part A of this question, you should certainly have a go at part B, because it's a show that question in A, so you could just use that answer from A to do part B. So same as before, we're going to do separating the variables. So first of all, I'll take my dt on this side, and then I could take the cube root of h on the left hand side, and now I'm ready to write as an integral. So we know the cube root of h, when you take out the top, it will be negative power, so it will be h to the power of a minus a third dh, and using basic integration we could work this out, because you're simply adding 1 to the power, dividing by the new power, and minus k is a constant, so when you integrate a constant, you just write minus kt, and then we have to make sure we just put plus c just on one side. And if I multiply both sides by 2/3 and cube both sides, so that gives me h squared, and then I could square root both sides. So we could further simplify this by swapping the order of the terms inside the bracket. And now we note that c is a constant, so 2/3 c, and we also note that k is a constant, so is 2/3 k. So we could replace 2/3 c with a constant, let's call it p, and 2/3 k with a value called q. So here we have it. So now we're told that initially the height of the water is 27 meters, and 10 minutes later the height is 8 meters. So we know it's decreasing because there's a hole at the bottom of the drum. We asked to find the values of the constant p and q. So when t is equal to 0, h equals to 27. So 27 is equal to p minus q0 to the power of 3 over 2. So if we simplify that, we could work out what p is, and that gives us p value of 9. Now we do the same thing. We're told when t is equal to 10, h is equal to 8, and we also know what p is now. So if we substitute this information in, and we simplify, we cube root both sides, and we square both sides, add 10q and subtract 5, and that will give us q equal to 0.5. So now we could write h equal to 9 minus 0.5t all to the power of 3 over 2. Now part D of this question, it says find the time in minutes when the water is a depth of 1 meter. So now we've got the formula for h. We want to find t when h is equal to 1. You just simply replace h with 1. We cube root both sides. We could square both sides. Subtract 9 and divide it by minus 0.5, so that'll give us t equal to 16. Alright guys, why don't you just pause the video and have a look at this exam question. Well, I hope you all had a good go at this question. Here's the answer for part A, part B, and part C. Alright, thanks for watching today's video. Please subscribe to my channel. There will be more videos uploaded every week.